Welcome to our final Comp 11 lecture. At this point, you actually know everything that you need to know to do your final project. Today, we're just going to wrap up some final object-oriented programming topics. Some of them may help you to prevent making mistakes in your final projects, and otherwise, a lot of the topics today are just additional features of OOP that you might see in the future or you might want to use in the future. So we're actually going to start today's lecture with just kind of a rundown of common errors that you'll probably see when you start working with multi-file programs. So getting through your final project without making at least one of these errors once is almost impossible because I made each of them at least 15 times. So we're going to have just a rundown of what these errors are and what the resulting feedback in the terminal looks like. So you can always come back to the start of this lecture if you have a bug in your final project that's just giving you fits. You can come back to this point in the lecture and check out this list and kind of rule out these things when you do your final project. So let's take a look. All right, so I've got terminal up on the left, and I've got Richard's demo from our last class up on the right. So that includes vector-tester.cpp, which includes our main function, the vector class, the card class, and the term-funcs class, which allows us to control the terminal screen. So the first common mistake that you're likely to make when you're building programs out of multiple files is that when you actually compile the program, you'll forget to type one of the .cpp files. So in order to compile this program, I need to compile vector-tester.cpp, vector-full.cpp, card.cpp, and term-funcs.cpp. So the common mistake is that I'll forget one of those. So here's a compilation statement where I'm running G++. I'm going to call my executable vector test, and I've listed vector-tester.cpp, vector-full.cpp, and term-funcs.cpp, but I've forgotten card.cpp. So if I run this, the compiler is going to be upset. It's going to be like, where is my card code? So in this case, you're almost certainly to get an error that mentions the linker. And so it's basically saying, look, both my main function and essentially the vector implementation relies on being able to access this card class. Where is my card class? So if you see an error like this where you get the red error, it says LD symbols, it says linker command failed, there's a pretty good chance that you either forgot or maybe misspelled one of the .cpp files on your command prompt. So again, the easy way to fix this is I can just add card.cpp to the command prompt, and now it's going to be perfectly happy, ready to run the program. The second common mistake that you might make is in one of your .cpp files to forget one of these scope resolution operators in front of one of your functions. So you've actually seen Richard do this in his demo. You probably saw me do it in my demo. This is the easiest mistake to make. So right now I'm in vector full. I have, let's see, what do we definitely use? Where's my size function? Here we go. So the size function is a function in the vector class that gets used a lot. So I'm just going to delete this vector : in front of it. Very bad news. So let's try to compile. Great, so error, use of undeclared identifier vsize, did you mean size? And so this is coming from line 51. So if we come back here, indeed, that is our size function. And so the error we get is actually, you know, the compiler is fine that you want to have a function called size, but size at this point is not in any way associated with our vector class. So the issue that it's telling you is that it doesn't know how to resolve the variable named vsize, because vsize was declared as part of the vector class. There's no variable of that name that exists anywhere else. So in your size function, when you say vsize, it's like, I'm totally fine that you have a size function. It's just that I don't know about any variable called vsize. So that's a common thing you'll see if you forget this scope resolution operator. Again, if I put it back in, compile it again, everything's fine. My other favorite flavor of this is if I take that scope resolution vector : here. My other favorite trick is to accidentally put that in the declaration in the .h file. So now instead of just a size function declared here, it's vector : size. They're not going to like this either, but they actually give you a very informative message about this. So great, so I've compiled it. Error, extra qualification on member size. And so it's pointing to exactly this line in my vector-full.h file, line 24, extra qualification, and you can see it has highlighted in green that vector : saying, please take that out. So again, I can take that out, save it, run it again, compile it again, and the compiler is much happier, I suppose. Last but not least, the other just common mistake to make is to change one of your function specs either in the .h or in the .cpp file and forget to change it elsewhere. So if I come into this .cpp file, let's say, this is our at function. So this is a function that's going to take in an index and return a data item from our vector. So let's say you're working on one of your class implementations and you decide that you need to change the function arguments. So I might change this to something like float and then try to compile it again. Everything seems fine from at least the perspective of my .cpp file, but this is the same issue as trying to change the signature of a function and forgetting to change the declaration up at the top. So I'm going to get an error, out of line definition, at does not match any definition in vector. So again, this is kind of the last final common mistake to make as you change the function specs somewhere and forget to change it elsewhere. So in this case, you get one of these out-of-line definitions, and it usually mentions something about matching. So if you see any type of matching error, it's usually a good idea to go back and check both your CPP function signatures, your .h function signatures, and then anywhere else in the code where those functions are being called and making sure that all of those function signatures match. So those are going to be your most common errors and mistakes that you make when you're dealing with these multi-file programs. So maybe write these down in a list, and when you're working on your final project, just have them handy for when you get a weird error that you can't quite figure out, to just run through these common ones and kind of tick them off as not being the part of the problem. So now we're going to move on to our 3 topics for today. The first is copy constructors, and then assignment operators, and then inheritance. And so again, these are all features of object-oriented programming. The first 2 of these may come into play for your final project, mostly in terms of just not making a specific mistake in your code. And then the last one is just kind of an additional feature that you probably won't need for your final project, but is worth knowing if you're ever going to be working with OOP again. So let's kick it off with copy constructors. The motivation for a copy constructor actually comes from an issue that Richard showed you all at the end of his last lecture. So to kind of recreate that issue, I'm in my vector tester.cpp file, and I'm in my main function, and we start main by pushing 13 cards onto the deck. So I'm going to keep that. I'm going to delete a lot of this extraneous pushing and popping that we did in the last lecture. So that's gone. And we're going to come down, so we're just simplified to pushing these cards onto the deck. We're then going to print the deck out and then free the remaining memory and be done. So let's just save that and make sure it works as intended. So compile and run the program. Here we go. So great. So it prints out all 13 of these cards that we added to the deck. And in theory, if I run this with Valgrind, I should get a clean slate. So great, no definitely lost memory and no errors. So right now we have a nicely working program. Now, the issue that Richard ran into was that he originally did not pass a vector pointer to this print card vector function. He had passed the original, just the vector. So let's recreate that. So we're going to pass not the address of the vector deck, we're going to pass deck itself. And then up in this function, instead of taking a vector pointer, it's just going to take the vector, which means that we can call all of these vector functions with the dot notation instead of the arrow notation. So vsize and vat should all be dot notation. So let's save this and compile it again. And now if I run it, let's see what happens. So it printed all of the cards seemingly without issue, but then I get this tragic error at the end. Malloc error break to debug, abort trap 6. pointer being freed was not allocated. So I think that's the best clue here. The disappointment that the program feels with me, and you get this a lot when you see these weird errors that are referencing something that looks like this, with like a 0 and then an X and then a bunch of numbers. That's usually how the computer writes a memory address. So when you see something like this, it usually means that you tried to do something at a memory address that you weren't supposed to be at. And in this case, it's talking about freeing memory. So the clue here is that there's something to do with an address and freeing. So the first inclination is that there's something going wrong with the delete statement. So this, in fact, is the case, and we're actually going to add a couple of debugging statements to this program just to get a sense of exactly what might be going wrong here. So we know that we get to this print card vector function all right, and that the cards all print all right, and that seems totally under control. So the question is, something goes wrong after this. So I print all the cards, that all happens fine, this function ends, and after the function ends, I do all of these card deletions from the deck, and then the function, or then the whole program at that point ends. So the question is, what goes wrong essentially after the print card vector function gets called, and specifically after the cards get printed. So I'm going to add a few debugging statements to see if we can narrow down what's going wrong and exactly when it's going wrong. So the first thing I'm going to add is a little cout statement here that says finishing the print function. Great, so little print statement there. I'm going to have an additional print statement here that says back from the print function. So this will let us know when we're leaving that print function, and then in theory we should arrive right back in main after that function returns. And then I'm going to add another print statement here that just says finishing the program. And I'm going to add one more print statement, and it's going to be in my vector destructor, because the mention in this error is that there's an issue with memory being freed. Well, at this point in the program, memory is only being freed in two places. One are these deletes, where I'm deleting the individual cards, and I've got that nicely sandwiched between debugging statements. So if anything happens here, I'm going to see one of these two cout statements, but not the other. The other time something's getting freed is in the destructor, where I'm actually freeing the vector itself. So I'm going to put another cout statement in here just so I know when I've actually arrived in the vector destructor. So I'm going to say in vector destructor. And I'm going to compile again, and this time I'm going to add the -g flag so I can run Valgrind. And I should see some debugging output that hopefully will help us out. So great, rerun the program. Again, we get the 13 cards printed, no issue there. And the first print statement we see is finishing the print function. So if I go back into my vector tester, that's happening up here in the print card vector function. So finishing the print function. Let's see what is the next print statement. Now it says in vector destructor. Okay, that's a little nerve-wracking. So now I'm in the vector destructor. I've reached the end of this function. I'm in my vector destructor. The next thing I see is back to the print function, or back from the print function. So that's happening here. So then after that, something goes terribly, terribly wrong. So what I can see is that I make it to the print card vector function. Those print statements that print the card execute correctly. I finish that function, but then I end up in the vector destructor, and then I'm back to my main function, and then something goes terribly wrong after that. So let's try running this a second time with Valgrind just to see if we can get any more indications of what's happening. Oh, woof. All right. What's going wrong first? So we've got vector tester, line 43. We don't like that. All right, so that's happening here. And it doesn't like this call to the at function. So something about, it's not mad, it doesn't look mad about trying to free the actual card that's there. It's just mad that we're calling this at function at all. Something is going wrong, it looks like, in the at function. So to get a better sense of what's actually happening here and why we're seeing this pattern of we're going to this function, the function's ending, then we're ending up in the vector destructor, and then we're ending up back in main. And after that, after we're back in main, when we call the at function on our deck, we get this catastrophic error. So let's break down exactly why this is happening so that we don't accidentally make this mistake in our own code. You should be familiar with this picture by now. So same picture, slightly different code. So I've kind of replaced in a simplified version of our vector code. So we have a main function that declares a vector, pushes one item onto it. In this case, we're doing a vector of ints. And then I call some function past that vector directly to the function. Here's the function where I just print out that first element, the element in the first index of the vector, the function returns, and then the program returns. So this is my entire program. So if we split this off into the main function in pink and the function that gets called in green, surely you're aware that as this program progresses, the first thing that's going to happen is that we always start with the main function. So main gets pushed onto the stack. Main is going to call function 1. Function 1 is going to get pushed onto the stack. When function 1 finishes, function 1 is going to get popped off the stack. And then when main returns, main is also going to come off the stack. So the question is, why does this create a problem when we're now working with vectors? So let's take a closer look at this main function. So that goes onto the stack, and along with it goes its arguments, which would be argc and argv, and in addition to that, any variables that are declared in main. In this case, one of the variables declared in main is this vector. And with that vector comes all of its data fields that are declared in the vector class. So in the stack, we need to make room for this vector, which means we need enough room for the vector's size, the vector's capacity, and the pointer for vbuffer. So we need a space big enough to hold the address of vbuffer. Because if you remember, vbuffer is the actual array that's working under the hood of our vector, and so vbuffer is actually just a pointer to an address on the heap that holds the actual array in this program. So fine, here's our main stack frame. We've got a vector on it. The vector has these 3 fields that have to take up space on the stack, and then one of these fields is a pointer that's pointing to the actual array that's in the heap. So what happens when we then pass this vector v to function 1? So function 1 is going to get popped onto the stack when it gets called. And so it is going to get passed as its argument that vector v. And so in the same sense that v is a part of main stack frame just as a local variable declared, v is going to be a part of function 1 stack frame, in this case though as an argument that's been passed to it. Now, we know that these arguments can be passed in 2 ways. They can get passed by value or passed by reference. So if you're dealing with a primitive data type, an int, a float, a character, those are always going to get passed by value unless you explicitly pass them by reference with a pointer. So if I pass an int to a function, what's going to happen is a copy of that int is going to get made and sent to that function. If I pass a character to a function, a copy of that character is going to get made and sent to a function. By contrast, if I pass an array to a function, that default is passed by reference. So the function is not going to get a copy of the array, it's going to get a pointer back to the original array. So the question here now is when we're declaring these custom objects and custom classes and we pass an instance of one of those objects to a function as an argument, does it get passed by value or does it get passed by reference? The answer is that it gets passed by value, but in a very kind of shallow way. So it gets passed by value in the sense that the function, so in this case function 1, is going to get a copy, its own private copy of the vector that's passed to it as an argument. So as you see in the stack frame for that function, it's not a pointer to the vector that it gets the actual vector in its 3 fields. So in the stack frame for function 1, as the result of being passed that vector argument, it now has room in its stack frame for v size, v capacity, and v buffer. The kicker is that when this copy gets made, it is literally just a copy and paste of exactly the content on the stack frame in the main function to the stack frame in function 1. And so literally the contents of v size is copied into the contents of v size in function 1. The contents of v capacity in the main stack frame is copied into the capacity variable in the function stack frame. And crucially, vBuffer is literally just holding an address. And so just like the other two fields, that address just gets copied into the address value in the function 1 stack frame, which means that in the function 1 stack frame, vBuffer is pointing to the exact same location in memory as the original vector in our main function. So we refer to this again as a shallow copy, where it's kind of like the program, the computer is not really thinking about any logistics beyond just copying and pasting the data in this vector data element from the main stack frame into the function 1 stack frame. The consequence of this is that this address gets copied over just like the size and the capacity. It's just that the address is pointing now to the exact same location as the original address was in the copy of the vector that's in the main stack frame. Now, for the duration of function 1 running, this isn't that big of a deal, but function 1 quickly ends, which means that the function 1 stack frame is going to get popped off of the stack. When that gets popped off of the stack, all of the variables associated with it are going to go out of scope. Just like any normal function that finishes and is getting popped off the stack, all of the information associated with it is going to go out of scope. So that includes any local variables, and that includes any arguments that the function took in. And so in this case, we have this copy of the vector object that was sent in as an argument and is now going out of scope. So as soon as function 1 is finishing and that vector argument from it is going out of scope, the destructor for the vector class is going to get called on this copy of the vector. The difficulty is that this copy of the vector is holding the exact same address of vBuffer as the original vector. So when that destructor gets called, that destructor, its only job is to delete the memory that vBuffer is pointing to. So when that destructor gets called, when the function ends, vBuffer and the memory associated with it gets completely deleted from the heap. So now that address, vBuffer address, is pointing to deallocated memory in the heap. Memory that if you try to access again, you're going to get a problem, which is exactly what's going to happen. So the function ends, function 1 ends, its stack frame gets popped off, that destructor has already been called because the vector is going out of scope, and now we're back down in main, and main has its own copy of this vector with its own copy of v size and v capacity and its own copy of the address. It's just that the address and the location that it points to is now pointing to deallocated memory. So now if I try to do any operation on this vector that involves vBuffer, segfault for sure. So I'm trying to operate on deallocated memory. So if you recall in our demo program, that's exactly what's happening when we get this catastrophic error. We return from the function, and the next thing we're trying to do is loop down that vector and deallocate the memory for each card. But to just get the card, we have to get that card element out of the vBuffer array. And so we're trying to access the vBuffer array to get a particular card element at a specific index. It's that at function that's causing the problem. And the problem is that we're trying to access an array at a particular index in the heap. It's just that all of that memory on the heap where that array was supposed to exist has all already been deallocated. It got deallocated by the destructor of the copy of that vector, the shallow copy that got sent to the function. So that's why the at function causes this catastrophic meltdown. You're trying to access an array at a specific index, but that array has already been deallocated on the heap. It doesn't exist anymore. That's also why this problem is completely solved by, instead of just passing the vector directly to function 1, to pass a pointer to the vector instead. And so this is how Richard solved the problem in the last lecture. So in our main function, instead of just passing v to function 1, we're going to pass the address of v. And in function 1, instead of expecting a vector, we're going to expect a pointer to a vector. So the setup in main is going to be pretty much the same. A vector is still a local variable in main, so the vector will still appear in the main's stack frame with v size, v capacity, and v buffer. The difference is that when function 1 gets called, it's not going to get a copy of this entire vector. It's not expecting to get a copy of this entire vector. It's only expecting to get an address. And so in the function1 stack frame, all we get here is an address, and it's the address of v, so it just points down to where v is in main's stack frame. So as you can see, just based on the arrows, this has no bearing to the address that vBuffer is pointing to. There are not two places on the stack now pointing to that same spot at memory, so we don't run any risk of that memory getting deallocated by accident when the variables in function1 go out of scope. When function1 finishes, all that's going to go out of scope is the variable holding a pointer, and a pointer does not trigger a destructor to be called. It has to be the object itself going out of scope to trigger the destructor. So function1 is going to finish, go out of scope, and main is still left intact with vBuffer still pointing to usable allocated memory on the heap. So this is one workaround to this issue, is to always pass around pointers to objects when you're passing objects of particular classes to and from functions. However, the copy constructor is what offers a workaround to this that'll allow you to still pass the objects directly to functions without having to worry about this deallocation issue. So let's see what a copy constructor looks like. So as the name suggests, a copy constructor allows you to specify exactly how to make a proper copy of an instance of the class you've declared. So this is the constructor that's going to get called by default whenever you need a copy, particularly in the situation where you're going to pass an instance of an object to a function. And again, the operating system is going to try to pass that object instance by value. So it's going to try to make a copy of it. Its default way of doing this is a very shallow kind of not very logically deep way. So the copy constructor provides you with a chance to specify actual instructions for how to make a copy. So in situations like this, those instructions will just defer over to the copy constructor. So if I'm in my vector full.h file, the copy constructor looks like any other constructor, as in it's just the name of the class followed by 2 parentheses. It's just that the copy constructor has a special argument signature that sort of flags it as the copy constructor. Now, since the job of this constructor is going to be to create a new vector, but based on a copy of another one, it should come as no surprise that the argument it takes is a reference to another vector. So the copy constructor takes in a vector as its argument, and this is the vector that it's going to try to make a copy of. Now, the way that this argument is specified is about as weird and annoying as it possibly could get. This is like all of the oddities of C++ crammed into maybe like 10 characters of code. So the first thing is this constant piece. They're just saying that once you pass this argument into the vector constructor, you're not allowed to change it. So you're not allowed to change the vector that you're making a copy of, which on some level makes sense. And this notation, the ampersand variable, is a C++ shortcut to pass by reference. So this basically says that this vector is being passed by reference, but it still allows you to interact with that vector as if it had been passed by value in your function, which we'll see in a second. So again, you probably won't even have to write one of these this semester. Just if you do, you'll have to Google this copy constructor argument syntax, because I essentially have to do it every time I'm going to write a copy constructor. So that's going to be the function signature, and now we just need to specify the function in our vector full.cpp. So I'm going to grab that signature, come over here, I'm going to put it right below our normal constructor, and here we go. So the game plan here is I'm being given some vector as an argument, and the question is how do I properly make a copy of it? Now, some of the fields are easy to copy. So if I look back in my .h file, here are the fields that I have to deal with: the capacity, the size, and the buffer. Now, the capacity and the size are the easy ones. These are just ints, and even making a shallow copy is sufficient to copy those values over correctly. It's actually the vBuffer, the underlying array itself, that you have to do something interesting with. And so this is the whole point of the copy constructor, is to specify these instructions for how to make what's known as a deep copy of your object. So in this case, the first couple steps are simple. So the v size of the vector can just be equal to the v size of the vector I was passed. And the same thing for v capacity. we're gonna make, I mean, you could make the argument that we don't need to copy over elements beyond what v size is, but we're gonna make a true copy of this vector. So we're gonna copy it as exactly as we possibly can. So those are the easy ones. We're just gonna create a vector with the same size and the same capacity as the one we're making a copy of. Then for our own new copy of VBuffer, we actually have to make that copy kind of manually. The same way you would do if you were actually dealing with a normal array and you wanted to add one element to it, you would have to make a whole new array, copy in all the original elements, and then add in the new element. So we're essentially going to do the same thing with VBuffer. So we have to make a new VBuffer, and we know that it's going to be of the same length as the vector we're making a copy of. So we can just use v capacity here. And then we just need to copy over all of the data elements. So that's just going to be a loop. So from I equals 0 to the v capacity. And in this case, I am just going to say that VBuffer at that index is just going to equal v's VBuffer at that index. And we're allowed to sort of refer to these private fields of the vector directly because we're working from the copy constructor within the vector class. Normally you wouldn't be allowed to do this in outside code, and this is being passed in, so it's a little strange, but in the copy constructor you're allowed to do this. So again, the VBuffer in this case is just holding these card pointers, so we can sort of directly copy over each of these individual indices from the underlying array, from the vector that we're trying to make a copy of to our new vector. And that's really all there is to one of these vectors. So once we've done this, we should have kind of an exact copy of the vector that we've been passed in. So we can actually check this to see if it compiles nicely. It did not compile nicely. Let's see, why is it mad? Oh, shocker, I forgot my scope resolution operator again. So let's get that in, compile again, much happier. All right, so now we can actually run the program. So let's go back and just look at main to make sure we understand exactly what was going to happen here. So again, we push these 13 cards onto the deck. We have a little print statement after each of those. And then immediately after that, this print card vector gets called, which kicks us up here. So that's going to print each card. It's going to print that it's done. And then it comes back, prints that it's back. All the memory gets freed, and then the program finishes. So let's see when these things get called. Actually, I'm going to add one thing to my copy constructor, which is just going to be a print statement saying that I'm in the copy constructor, so we can see exactly when that gets called. All right, so recompile and run it. All right, so the good news is that we didn't crash, so that's huge. So let's look back up at the top. So we have our, if we go back to vector tester, we have all of these. The vector has 1 element, 2 elements, up to 13, so that's this code being called. And then the next thing that happens in our main function is print card vector gets called. And so you can immediately see that if we kick up to print card vector, before it starts actually printing out the cards, we see this call to the copy constructor that happens automatically when I call this function and pass the deck directly. So in this case, I'm passing the deck by value. The default is that it should be passed by value when you're just passing that regular object, not a pointer to that object. So that gets passed by value, and then instead of the computer making kind of this default shallow copy of the deck, the copy constructor gets automatically invoked. The copy constructor is the one that is in charge of making this copy of the deck that gets sent to the print card vector function. We've written our copy constructor to make an exact copy, and so you can see that call happening here in the copy constructor. So then all of the cards get printed per usual, which leaves us saying finishing the print function. So that's us finishing the print card vector function up here. So we kick back down to here. And then as soon as the function ends, we see the vector destructor being invoked. So that's now the copy of the vector getting deallocated, which has its own pointer to its own set, its own instance of that array in memory. So now when this destructor gets called, it's not affecting the v buffer of the original vector. It's only affecting the v buffer of the copy, which is what we want. So now we see back in the print function, finishing the program, which happens way down at the bottom here, and then we see the vector destructor get called for our original vector, and again it has its own original copy of vbuffer, so there's no issue deallocating or accessing that memory to delete it, because it's the copy already was deallocated and was pointing anyway to a completely different area of memory. So that's the copy constructor. It allows you to pass objects directly to functions without passing them via a pointer. So you would really only want to do this if, number one, your class has dynamically allocated memory on the heap. If it doesn't, then a shallow copy of your object is probably good enough to pass to a function. So you don't have to worry about this deallocation issue when the function finishes and that copy goes out of scope. So number one, your class must have dynamically allocated memory in the heap. And number two, you would really only need a copy constructor in situations where you want the function to modify the object in a way that you don't want to be seen when you return back from the function. Because in all other cases, if your function just needs to read the object, or if the function just needs to change the object, but you want to see those changes when you get back to the calling function, you should just pass a pointer to that object, not the object itself. But if the function needs to actually modify the object, and you do not want to see those changes, those modifications when you return back from that function, then you really need to pass the object itself, and you need to pass a copy of the object itself. And if that object has dynamically allocated memory, you need to pass it via the copy constructor, where you can specify actual instructions for making that copy correctly. So that's the gist of the copy constructor. If you look here, our print card vector function does not need to modify this vector in any way. It's just printing it out. So we're going to go with the better approach here, which is to just pass it in as a pointer. And then we don't have to worry about the copy constructor being called or anything else. So actually the address goes here, and this should be vector star. And we can compile this. And I get a bajillion errors because I'm using dot notation instead of pointer notation to call these vector functions. And if I run this again now, we're right back to where we started, where the program finishes. We get back from the print function. Only one vector gets deallocated because we passed a pointer to it to the function. And if we look back up, the copy constructor never gets called because we're only passing that vector as a pointer to the function, not the vector itself. So that's the copy constructor. Let's take a look at the slight variant of this that we're covering next, which is the assignment operator. So the assignment operator is essentially addressing the exact same issue, just arrived at in a slightly different way. So here's how the same issue can get created in a slightly different way. So say we have a main function. In this case, this is something similar to our vector tester function, where it can interact with the vector class. So we're going to declare a first vector, v1. We're going to assume that the vector is going to contain integers. So we're going to push a couple integers onto the vector. So we're going to push a 7 onto the vector, and then push a 10 onto the vector. So the vector now has content. vbuffer under the hood has 2 entries in it. Then we're going to create a second vector, so v2, and then we're going to pull this trick, v2 equals v1. Now, the intent of this is fairly clear. It's like we want v2 to exactly equal v1, but again, we're at the exact same situation where v1 includes this pointer vbuffer to dynamic memory on the heap. And so if we just leave this up to the computer to deal with this instruction, it is again going to create a shallow copy of v1 and assign it to v2, which means that the address that v2's vbuffer is pointing to is the exact same piece of memory as v1's vbuffer. So if you modify or deallocate v2, those changes are also going to propagate to v1, just because they're both now pointing to the same piece of memory. This is the exact same issue that we saw in the last example when we were trying to pass a vector to a function, and a copy of that vector was going to try to be created. And again, without explicit instructions, it's going to be a shallow copy. So exact same scenario with the assignment operator. You have to specify explicit instructions for how to make a copy of v1 so that it can be assigned as the value of v2. Now, if the copy constructor involved some awkward syntax, the assignment operator takes it like 3 levels deeper. So I'm not even going to try to justify the syntax of how to specify one of these assignment operators. I'm just going to show it to you. If you ever need to use one, you'll probably need to Google it, just like I did in order to write this today. But really the important takeaway is that you understand why we need this assignment operator, which is to specify explicit instructions for how to make a copy of your object when one of those equal assignments is being used. So hang on tight, here we go. So here's the declaration for our assignment operator. It is pretty gross. Again, I'm not going to even attempt to justify why this syntax has to be the way it is. You just need to kind of look it up and use it when needed. And so long as you conceptually understand what it's for, you're in good shape. So here's the declaration in my vector.h file. So I'm going to come over to our vector full. I'm going to put it right below our new copy constructor. And because I am not going to forget that scope resolution operator again, so that's where the scope resolution operator goes here, which is just as painful as every other aspect of this. So the one thing that's unique about the assignment operator as opposed to the copy constructor is, as you can see, it wants to return an actual reference to the copy vector. So we have to actually return the copy. So the assignment operator is always going to end by returning a dereferenced version of this. So that's what gets returned at the end of that. And otherwise, again, you're just, same as the copy constructor, you're just specifying instructions for if you want to assign the value of one object over to another, how to make that copy so it's not just a shallow copy. And the good news here is that the strategy for doing that is exactly the same as it was in our vector copy constructor. So we're going to just copy over this first part. So this is us just copying the size and capacity and getting a pointer to a new chunk of memory of that same capacity on the heap. And then just as before, we're going to copy each element from the source vBuffer into our new vBuffer, and that's going to be our strategy again for the assignment operator. So if I set one vector equal to another, the process of copying that first vector, I want it to be exactly the same as we did in the copy constructor. So let's actually put this to the test and see if it works. I'm going to go back into my vector tester. So here's our print card function that we just messed with. And so before we get there, I'm going to declare another vector called dec2 in this case. I'm going to set dec2 equal to dec1. And then just to make sure that they're different, I am going to push an extra card onto dec2. So I'm going to create a new card. We'll make it the 30-second card in the deck. And I'm going to say dec2 push back and push the card pointer on. So now we initially set dec2 equal to dec1. So that should actually call our assignment operator. In fact, let's put a little cout statement in here so we can actually see when this gets called. In assignment operator. Great. So that should get the assignment operator called. So we should actually get a deep copy of dec assigned to the value of dec2. And then we're going to push this new card onto dec2. And then we're going to print both of these decs. And I'm actually just going to say which deck I'm printing first so we can tell. Printing dec. And then we're also going to print out dec2. And let's see what we get. So compile. All right, vector test. All right, let's start at the top, somewhere way up here. All right, so I'm adding my elements to the vector. This is to the first vector, our dec vector, so that happens up here. So then the next thing that happens is I declare my new dec and set dec2 equal to dec. And as you can see, I get a call to my assignment operator because that assignment is taking place. Then I push this card, the 30-second card, onto dec2, not onto dec1. And the first thing I do is I print out deck 1. So when I print out deck 1, I should just see those same original 13 cards that just is sort of the first suit, the spades, going all the way up to the ace. And so great, that's what we see. And then next I'm printing deck 2. So now I should see that same set of cards plus this extra card at the end. And sure enough, I see the entire set of spades all the way up until the ace, and then I see one additional card, which is this 32nd card that I pushed in. And then we see 2 calls to our vector destructor, which is both of these vectors going out of scope and the destructor getting called. So great. So again, solving the same issue with an assignment instead of a pass to a function with the assignment operator. But here's where things get a little sticky. Let's run Valgrind on this. Valgrind. All right, so I have no errors, which I like, but if you'll notice, I definitely lost 8 bytes of memory. Well, okay, where are those 8 bytes coming from? So if we actually look back into our vector tester program, so we've kind of decided that our deep copy for both our copy constructor and the assignment operator, if we go and look at the copy constructor and the assignment operator, we're making a new copy of VBuffer. So whenever we make a copy of one of our vectors, we are creating a new kind of array memory piece in the heap. But then we're just kind of populating it with exactly the same content as was in the original VBuffer. And this is true for both the copy constructor and the assignment operator. So VBuffer gets a new chunk of memory in the heap, but then its contents are copied directly in from the original VBuffer. Now, if you recall, the contents of these decks are these card pointers. And so the issue here it sort of depends on how you're using this, is that each of these cards gets allocated on the heap, but we're just kind of copying over the card pointers. So based on how we've set up these copy constructors and the assignment operator, the new deck is getting a new kind of array allocated in the heap, but that's containing the same pointers as the original deck. And so it's actually pointing to the same set. Those pointers are still pointing to the same set of cards in the heap. So the question is then, how do we free this up cleanly? Well, if we look, we're already freeing up all the cards in the first deck. So in this case, these are all the cards that got allocated with these new calls up here. And so when we do this assignment operator, deck 2 is getting all the same pointers as deck 1. And so all of the original pointers from deck 1 are getting freed in this piece of code. If we tried to execute this same piece of code for deck 2, we should get a problem, because then we're trying to free some of the same memory that's already been freed because it's the same card pointers as deck 1. So let's actually see that happen. Deck 2, we'll just do the exact same code but replace it with deck 2, recompile, and run the program again. We'll run it without Valgrind. So again, we get that same issue that we saw before, where we're trying to free memory that's essentially already been freed. So if we look, though, we don't have to free all of the cards in the original deck. The only new card that got created when we made deck 2 was this new card pointer that we pushed onto the end. So we can actually get away with 2 things here. One is that we could just delete card P, because that's still holding a pointer to that card that got created. So this should work. And if I run it, everything works out nicely. The other option that I can do here is I can say, I know that this last card that needs to be deleted is at the back of deck 2. So I can also say here, instead of delete card P, I can say deck 2 dot at say deck 2 dot size -1. So that's the last card. So this should also work, because the only card at this point that hasn't been deleted is the last card in deck 2, and we have 2 pointers pointing to it. We have that last index in deck 2 pointing to it, as well as card P. So we should be able to use any of those pointers to free up that last chunk of memory. Let's see, and run it. So that looks good, so let's Valgrind it just to make sure. And Valgrind is happy, so we have 0 bytes lost. and 0 errors. So we were able to free up all the cards that we created, which included these 13 original cards, as well as this one additional card that got added to deck 2. So we're currently running clean, and that's the gist of an assignment operator. The last item on the docket today is the concept of inheritance. Now, I'm only going to cover this mostly at a conceptual level because I don't foresee you needing this on your final project, but it is one of the coolest features of object-oriented programming, and it'll probably come up either in a future class or if you're building a program on your own. So it's something to at least be aware of and be exposed to once so that you can kind of dive in with more detail when you actually need to implement it. So the setup for inheritance today is we're going to imagine that we need to build a program that's going to help a boat store manage its inventory. So this is a store that's going to sell boats, and we're going to build them a program that's going to help them with inventory. So we're going to need some internal representation of a boat. So this makes a great case for a boat class. So building a class that can represent a boat and store information about boats, much like the dog class we've seen, and perhaps a little bit like the vector class that we've been working on for the past couple lectures. So when I describe a boat, you're probably picturing a glorious boat like this one, but you might also be thinking of a less glorious boat like this one. So the main issue here is that there are kind of two distinct types of boats, sailboats and powerboats. And in some regards, they share a lot of properties. So if you're talking about storing properties of these boats, both a sailboat and a powerboat is going to have some overall length of the boat. It's going to have a width, which is usually referred to as the beam of the boat. So that's a property that both a sailboat and a powerboat would have. They're going to be painted a certain color. So that might be a property that is shared both with sailboats and powerboats. But at some point, the similarities start to diverge, and sailboats and powerboats have properties that apply to one of these types of boats, but not the other. So with a sailboat, you might have a feature that describes the height of the mast. You might be keeping track of a sail count, so how many sails are coming with the boat if you buy the boat. Whereas on the powerboat side, there are a lot more specs regarding the engine, so you might need to keep track of something like horsepower. So this kind of prevents a nice implementation based on what we know so far. Our options are either to create one boat class and then have in that one boat class, so if I'm representing a sailboat, I would still have this horsepower element or field, even though sailboats don't really have a horsepower. And similar, if it was a powerboat, it would have a mast height and a sail count, even though those things don't really apply in any way to a powerboat. So one option is just to have one boat class, but it would have, for any boat you're representing, some fields that really don't apply to it. The other option is to split this into two classes, so maybe a sailboat class and a powerboat class, or a gross boat class, if we will. But then the difficulty there, now each class is specialized to the type of boat that we're talking about, but they're going to share a lot of properties. So they're both going to have length and beam and color, and so we're kind of duplicating information in a lot of places. So this is exactly the problem that inheritance is designed to solve. What we can do is we can take a situation like this and create a class structure and an inheritance structure where both sailboats and powerboats are able to inherit properties from a single, we would call this a superclass, that just represents the basic idea of a boat. And so the idea is that we would have one class that just represents kind of generally a boat. And so this class would contain all of the features that are shared by any boat that you might have. So in this case, that would be the length, the beam, and the color. And then both the sailboat class and the powerboat class, or the gross boat class, would not only be able to inherit properties of the boat class, but then they could kind of augment the features of a boat with the fields that are actually pertinent to either sailboats or gross boats, respectively. So our sailboat subclass could now have the mast height and the sail count fields, and the powerboat class could have the horsepower field. And so with inheritance, what we are able to do is to create these class structures where we have a superclass, in this case the boat class, that has properties that are going to be shared by all boats, And then we can have subclasses that kind of specialize based on that superclass. So you can imagine a similar scenario where we have an animal superclass, and then we can subclass that into animals like dogs or cats or fish. So the same idea here. So the one kind of key programming feature that comes up when you're building one of these superclasses that is going to be inherited by subclasses is that you get one more category of data fields and functions that you can deal with and specify. So just like our normal classes, if we're going to build this boat superclass that generally represents a boat, we can still have public functions and fields that can be used and accessed by any other code. And we can still have private classes and fields that can only be accessed and called by direct members of the boat class. However, when we start working with inheritance, we also get a third kind of class of functions and data fields, which is called protected. So a protected field can be used not only by boats, but by any subclass of boats. So if we define subclasses of sailboats and gross boats, these would be still able to access any protected fields or functions of the superclass, in this case a boat. So if we actually kind of look at how we would specify this, if we're going to specify a boat class, we would have, maybe a constructor, and we would have getters and setters for both the length, the beam, and the color. And then we would have these protected fields that are the fields of the boat, the length, the beam, and the color, but they're protected. So outside code can't access those fields. So if I'm in my main function, I can't just directly access and manipulate a boat's length. However, because they're protected, that means that any objects of a boat's subclass would be able to access these fields. And so the way we would specify a subclass looks like this. So if you notice at the top, we're going to have a class called sailboat, and then that extra public boat indicates that it's going to inherit all of the properties of a boat. And so again, maybe we have a specific sailboat constructor, and then we have getters and setters that are just specific to a sailboat. So we'd have getters and setters to the mast height and the sail count. And then we'd have some private fields that are specific to the sailboat. So the mast height and the sail count, again, aren't accessible by outside code, but are accessible within the sailboat class. And so by adding that public boat up at the top, that allows a sailboat to inherit all of the properties of a normal boat. So if you declare an object of type sailboat, you can not only use the getters and setters that are defined in the sailboat class, but you can also use the getters and setters that are defined in the boat class. And additionally, so we can also define another subclass for the gross boats, in this case the motorboats, that has kind of the same structure. So in this case, a motorboat only has horsepower is the only field we've talked about that's specific to a motorboat. And so you'd have a getter and a setter for horsepower, but if you declare an object of type gross boat, you also get access to the length, the beam, and the color fields, as well as the getters and setters from the superclass, the boat class, that are associated with them. So the one critical realization when you're doing these subclasses is that a sailboat is a boat. So if a boat is a superclass and a sailboat is inheriting from that boat class, then a sailboat is technically a boat. But a boat is not a sailboat. So what that basically means is that you can do something like this. So you can say declare a sailboat S and then say boat B equals S, because a sailboat is a boat. But you would not be able to do this the other way around. So you wouldn't be able to declare a boat and then set a sailboat equal to that boat. So that's the basic idea of inheritance. That's really all we're going to cover today conceptually. There are a lot of cool features that you can do with inheritance, like you can specify, if we go back, if you notice, for both the sailboat and the regular boat, we have a constructor declared. So there are a lot of cool ways that you can play off these functions that have similar functionality in both a sailboat and a boat. So you can have a sailboat constructor do some specialized setup of the sailboat and then defer to the boat constructor to get boat-related general setup done next. And there are a lot of cool little features that allow you to really manipulate this relationship of inheritance. But overall, what it allows you to do is kind of simplify your code so that you don't have a class that has unnecessary fields in it, and you also don't have to have two classes that share a lot of the same fields. So again, if you encounter this when you're writing a program of your own, the textbook has a great section on inheritance. And this is probably a concept that you'll use much more directly in Comp 15, so it's worth just being aware of in case it comes up in either something you're writing yourself or something you're definitely going to see in a future class. So that's it for inheritance and for new topics in Comp 11. We'll see you to do Splendor Q&A and final Q&A in our remaining lectures, which are on our course calendar schedule. But otherwise, happy final projecting. I hope you like the game Splendor.